Hey everyone! Have you ever thrown a stone into a still pond? You see those beautiful ripples spreading outward, almost hypnotic, right? Now, have you ever wondered, does the water actually travel across the pond? No. Only the disturbance moves, that's what we call a wave. A wave is basically nature's way of transferring energy without transferring matter. The water doesn't go anywhere, but the ripple of energy does. Mechanical waves, like sound or water waves, need a medium. Air, water, or even a stretched string. But light waves, they're total rebels, they don't need any medium at all. In every wave, particles of the medium just vibrate about their fixed positions, passing energy along, like a stadium crowd doing the wave. Nobody moves seats, but the excitement travels across the stands. Now that we know what a wave is, let's peek into how they behave. When a wave moves through a medium, the particles can vibrate into different ways. And that gives us the two celebrity types of mechanical waves, transverse and longitudinal. In a transverse wave, particles move up and down while the disturbance moves sideways. Think of flicking a rope. The wave travels horizontally, but the rope itself moves vertically. In a longitudinal wave, the particles move back and forth in the same direction as the wave. That's how sound travels through air. Molecules bunch up, compression, spread apart, rarefaction, and pass the message along. If you could see it, transverse waves look like a sine curve, while longitudinal waves look like traffic jams moving down a highway. Alright, let's dive deeper into transverse waves. Imagine shaking one end of a rope up and down. The motion you see along the rope is a perfect example. Each particle moves perpendicular to the direction of travel. We represent this mathematically as y of x and t equals a sine of kx minus omega t. Here, a is amplitude, how far the rope moves up and down. K is 2 pi divided by wavelength lambda, and omega is 2 pi times frequency f. Crests are the peaks, like hills, and troughs are valleys. These alternate as the wave moves. Interestingly, transverse waves can only travel in solids and on liquid surfaces. Gases just can't support the sheer motion. They're too loosey-goosey. Now, let's talk about longitudinal waves, the ones responsible for sound reaching your ears right now. Here, particles move back and forth in the same direction as the wave. We express it as S of x and t equals S sub m sine of kx minus omega t. S sub m is the amplitude, the maximum to and fro distance of particles. When the particles crowd together, we get compressions, regions of high pressure. When they spread apart, we get rarefactions, regions of low pressure. Take a slinky spring, push and pull one end, and you'll see compressions moving along the coils. That's exactly how sound travels through air, molecules jostling forward and backward to carry the tune of your favorite song. So far, both types of waves seem different, right? But here's the twist, mathematically, they're siblings. Whether it's transverse or longitudinal, the general form of a wave is 11 of x and t equals 11 sub m sine of kx minus omega t. For transverse waves, 11 means vertical displacement y. For longitudinal waves, 11 means forward displacement s. And the relationship between speed, frequency, and wavelength? Simple but powerful. The velocity v of the wave is equal to angular frequency omega divided by the wave number k. It is also equal to the product of wavelength lambda and frequency f. That means the faster the vibration, higher frequency, or the longer the wavelength, the faster the wave moves. Alright, time for some math magic. Let's find how fast the particles themselves move. We start with the wave equation, y of x and t equals a sine of kx minus omega t. To get velocity, we differentiate with respect to time. That gives v sub y equals partial y by partial t equals minus a omega cosine of kx minus omega t. The negative sign? It just means the velocity is in the opposite direction to displacement at that instant. The maximum velocity is a times omega, the product of amplitude and angular frequency. And here's a fun insight, the particle's velocity leads its displacement by 90 degrees. So when displacement is zero, velocity is maximum, like a pendulum passing through its mean position. Waves are nature's elegant way of transferring energy without moving matter. Transverse waves, think of a plucked guitar string, the motion is up and down. Longitudinal waves, like sound, the motion is back and forth. Both obey the same wave equation, xi of x and t equals 11 sub m sine of kx minus omega t, and both travel at a speed given by v equals lambda multiplied by f. Whether it's ripples on water, sound from your headphones, or even seismic vibrations beneath your feet, everything around you is waving. So next time you drop a stone, strum a guitar, or hear thunder rumble, remember, you're watching energy move, not matter. Sign off, and that's the magic of transverse and longitudinal waves, tiny oscillations that make the universe sing. See you in the next session with another mind-bending concept of physics.